In the first three stages of cellular respiration, we stored energy in reduced coenzymes, NADH and FADH2. And I should say that obviously is in addition to what? What else do we store energy in as we go through the processes of glycolysis and pyruvate oxidation and movement into the mitochondrion, and then finally Krebs cycle. Yeah. Obviously, it's worth mentioning that this is in addition to ATP. Right? Because we've produced ATP along the way. When we get back to kind of these sketches, you should kind of in your brain be able to sketch out this process right now. If we start with a glucose molecule, what's the first process it goes through? Glycolysis. And when it goes through glycolysis, what's the end point of that? Sure, in terms of energy, we get 2 ATPs, and what else do we get? 2 NADHs. And what do we end up in terms of product? Yeah, 2 pyruvates, right? So we kind of immediately get this branching point where we have pyruvate, sometimes written as pyruvic acid. What has to happen to pyruvate next? So this is, we take glucose, which is this asymmetrical molecule. We put through the process of glycolysis, literally the breaking of glucose. And along the way, we take out 2 ATP and 2 NADH, a little bit of energy. This ATP can be used by the cell right away. These NADHs, well, we're going to talk about that today. Pyruvate, where does this all happen? I guess is worth mentioning. Where are we when this happens in the cell? Yeah, we're just in the cytoplasm. We're in the cell in general. Where does the pyruvate go? It passes into the... How many membranes is it going to have to pass through to do that? 2. Why is that? Where in the mitochondrion does it go? Into the matrix of the mitochondrion. Good. Along the way, what does it get converted into? Yeah, it gets converted to an acetyl group, which is a 2-carbon group. And it gets bound to an enzyme called coenzyme A. So acetyl-CoA, but really it's that acetyl group that we're looking at. Pyruvate had how many carbons? 3 carbons. Glucose had how many carbons? And acetyl has how many carbons? 2. So what happens in the middle here? We lose one in what form? Right, we get rid of CO2. We're going to kind of track those carbons as we go. And do we get energy here? Yeah, we get an NADH in terms of energy. You don't need to know every structure along the way of these, but you need to kind of be able to sketch this, sort of summary of what happens. So we also get an NADH. And of course, if we get an NADH on this side, since we're talking about a symmetrical process, we're also going to get one on this side. Then that acetyl-CoA enters into a cycle, which we call, the citric acid cycle, Krebs cycle, right? Goes through this cycle, this cyclical process. Once the acetyl-CoA binds on, sort of what's the start point and what's the end point? You do not need to know every molecule in here. You don't need to know that it goes malate, oxaloacetate. Yeah, but we should know that once the acetyl coenzyme binds on, it forms citrate or citric acid. And by the time it's done, what will it have formed? What's the end point that can then be recycled to start again? Oxaloacetate. And along the way, what's it going to lose? We're going to lose a CO2 here. And then immediately in the next step, we're going to lose another CO2. Right? That's going to happen here as well. Lose a CO2, lose a CO2. And for those of us keeping count, that's 1, 2, 3, 4, 5, 6 carbons gone. So that's all the carbon from the original glucose now accounted for, right? But there's still some energy to be lost. Overall, do we remember what we got here? I get the numbers messed up sometimes, but if I'm remembering right, both sides get 2 NADHs, an FADH2, and a GTP, which we said pretty much immediately gets metabolized into an ATP. Do I have those numbers right? Is it 2 NADHs or is it 3? Can someone check quick? Obviously, I need to study my metabolism pathways just like you guys do. Just one run through Krebs cycle. Is it 4? It's 3. Which one did I miss? Like, obviously, you guys don't know which one I missed. Oh, I forgot about the very last step. I was remembering these two where we lose the CO2, but I was forgetting the very last step where malate turns into oxaloacetate. That's right. So it's not 2 NADHs on each side. It is 3 NADHs. You want to kind of have very solidly this process in mind. Because, again, I'm not so concerned that you have each one of these structures memorized and its name. I'd like you to know that we go from oxaloacetate to citrate. I don't really care that you be able to draw that. I do want you to have a good sense of tracking the carbons, of knowing that way back in glycolysis, we start with a 6-carbon sugar and be able to say, like, okay, I know by the time we get to pyruvate, that's 2 3-carbon molecules. And then by the time we enter the mitochondrial matrix, now we're down to 2 carbons, and then knowing that they get lost early on in Krebs cycle, and know that each of those is tied to a dehydrogenase. And what dehydrogenases do is they take hydrogen off this molecule and slap it onto NAD, which turns it into an energy storage molecule. And that happens twice in a row. That's something worth mentioning too, though we're not going to mention it today. I don't expect you to know each of the enzymes by name, but I expect you to know what the dehydrogenases do. I expect you to know what the kinases do, and I expect you to know what the isomerases do, the basic class of enzymes. That kinases are responsible for taking phosphates off or putting phosphates onto ATP groups. That dehydrogenases are going to form NADH from NAD. So these are things we need to know as we go through this process to kind of have a good, solid understanding of how it works. So that serves as kind of a starting point for this. But now if you look, this can be used as energy by the cell right away. That can be used as energy by the cell right away. That can be used as energy by the cell right away. These need to be converted to ATP to serve as an energy source that's readily usable by the cell. So do these, and so do these. Now, if you were designing this factory, would you design the factory parts to convert these into ATP inside the mitochondrion, or would you have them go back outside the mitochondrion to do it? Just looking at the way things have gone so far, where would you put that next piece of machinery? What makes the most sense, given where most of your ingredients are? Inside the matrix, or inside the mitochondrion. Does that make sense? Because altogether so far, we have 6 NADHs and 2 FADH2s hanging out inside the mitochondrial matrix, and we have just 2 NADHs outside of it. Oh, sorry, 4 altogether. Though actually this happens as it's coming into the mitochondrion. So these are already available. These ones are not. These ones will actually have to be transported in, which is worth highlighting in a different color, perhaps. These will have to be moved into the mitochondrion. So, the plan now, or what we're going to talk about now, is the process by which the energy, the free energy in FADH2 and NADH gets captured in ATP molecules. So, today's process is how the free energy, what letter do we use for free energy, by the way? Yeah? Sorry, I'll get out of your way. FADH2 and NADH can be transferred to ATP. So basically what we want to do is we want to take NADH and oxidize it down to NAD plus with the H plus off of it, and we want to then use that energy coupled with a reaction that will take adenosine diphosphate and a phosphate group floating around in the mitochondrion and turn it into adenosine triphosphate. We want to couple these reactions. So as we've been doing all along, we want to be able to do this reaction, have there be a change in free energy. In this case, it'll be negative because that energy will be released to the surroundings. And then we want to couple that with this reaction so it can have a positive delta G and take that energy and store it as ATP. Because again, ATP is what we call sort of the cellular battery or the cellular currency of energy. So how do we do that? Well, we do it in the mitochondrion. And up till now, we've looked at the mitochondrion and we've talked about the fact that it has two membranes, an inner membrane and an outer membrane. What do we call the space between those two membranes? The intermembrane space. And what do we call the space inside the inner membrane, the innermost sanctum? I know I've mentioned it a couple times today already, the matrix. We also noted that the inner membrane isn't just a second envelope like this. It has this very pointedly folded structure. What do we call the individual folds of the mitochondrion? Cristae. Why do surfaces take on complicated folded structures like that mechanically? What's the purpose of that? What do we gain? Okay, I'm being told we gain more surface area. Why is that a benefit? Well, it's a benefit if what you're doing happens on that surface, right? We have a radiator work with lots and lots and lots of individual fins and folds because we need the surface of that to radiate heat off. The villi in our small intestine have many, many folds because it's the epithelial cells of the inner lining of the small intestine that absorb nutrients. So having lots of surface area does that. So obviously, that inner membrane must be important. But we haven't talked about it in previous lessons. We're talking about today. What we're talking about today happens embedded in the inner membrane of the mitochondrion. So we're just going to quickly remind ourselves what this looks like a bit more schematically. Here's the mitochondrion. Here's the inner membrane. So let's just quickly remind ourselves of the names of these things. We have the inner membrane. The outer membrane. We have the matrix. We have what we called what again? What's this space here? The intermembrane space. Intra is between, and inter is inside. So like intramural sports are inside your school, and intercom is inside of your house, which people don't have anymore because people just have cell phones now.
So it makes sense to say it's the intramembrane.
Or maybe I have that backwards. Sorry, no. It should Oh, give me a sec. Now I have to look that up. I'm all confused. Anyway, it's not what we're talking about right now. Not an English class. Though every class is an English class. So I'm going to get back to you on that. I think I might have just accidentally said that backwards to you. But here's what I really want to note. This right here is where what we're doing today takes place. What we end up with is we've got a section of the inner membrane we've got the matrix on the inside, which I'm going to color in blue just so we can kind of differentiate between them. I'm not going to color the whole thing now. I'll come back and do that after because I'm not quite that obsessive to waste all of your time. And we've got the intermembrane space here. And this is where today's activity is going to happen, where everything is going to happen using both of these spaces and using proteins embedded in the membrane, and some that sit on one surface or another. All right? So this is what today's work is going to look like. Krebs cycle, if you remember, happens in the matrix. Oh, there's no apostrophe. But today's activity happens between the matrix and the intermembrane space using the surface of the inner membrane, which is folded into cristae, as its sort of operating location. Can you kind of picture that? Because we're going to make reference to these spaces. I'm going to say it moves from the intermembrane space to the matrix, and it moves across the membrane. And it's helpful if we know what we're talking about in terms of geography. And what could possibly help things be more clear than beautiful art, right?
What about pure water? That's pretty clear.
So we have a double membrane in our mitochondria. To allow two separate fluid conditions to be separated by a semi-permeable membrane. Sorry, lots to go. I hear everything, except the intercom, which for some reason I can't hear even though it blasts into my ear, and I don't understand it. Teacher is basically a professional eavesdropper. The electron transport chain, which is what we're going to talk about today, happens using proteins embedded in the membrane. All right, take a minute, get that written down, then we'll move on to the actual business of this. And again, I didn't write inner membrane here, but can we all see from my beautiful diagram above that we're talking about the inner membrane, not the outer membrane? So the question is, how do you design a factory that can deal with a boatload of NADH and FADH2 all at once and just get the energy out of them? And the mitochondrion is that factory. That's why it's called the powerhouse of the cell. And it's a very clever design because it uses a fundamental principle of nature. And this is almost barely an analogy. I want you to think about this. We happen to live next to one of, the wonders of the world, Niagara Falls, my hometown. I like to think that if you go to every other wonder in the world, there's also like a casino parking lot right at the brink of it. I always think that about my hometown. I think if you actually go to Niagara Falls and you stand right at the brink of the falls, you're standing in a casino parking lot, because that's what we apparently think the most important thing is about our beautiful town. Tells you everything you need to know about my hometown. But having said that, it's just dumb. I just like to picture the Grand Canyon, and like, do they do that? Like everywhere there's a view, is there like just a neon billboard for like some place to go gamble? I don't know. I hate my hometown, but I think you're supposed to hate your hometown a little bit. I also love my hometown. So Niagara Falls is this majestic, amazing thing. And I gotta say, even though I grew up in Niagara Falls and I lived there my whole life and I worked down there for years, it still kind of takes my breath away. I don't know if you go there very often. You go to Clifton Hill maybe once or twice a year or something like that. But I don't know about you, but to me, like, even though you've seen this stupid thing probably your whole life, a few times a year, it never ceases to amaze me. You go stand there and you look at this thing in the casino parking lot. You can also be in the people mover parking lot or the restaurant parking lot. Those literally, like right at the falls, those are your three choices. Or if you go up the hill, the casino itself. And you can stand there, maybe between gambling sessions, I guess, I don't know. And it kind of takes your breath away. It's this majesty of just like this incredible volume of water, moving, and you think about the massive amount of force involved. And then if you think, it's actually not even most of the water. We're not even seeing the splendor of this thing as it would have been, because what do we do with most of the water that comes down the Niagara River? Yeah. What do?
Hydro.
Yeah, we divert it. We run it through a bunch of aquifers that run like underground under the city, and Niagara Falls, New York does the same, and we run them to a generating station. Like, it's not like there's turbines at the bottom of the falls. We have down river at Sir Adam Beck 2 on our side and NPG, Niagara Power Generation Station, on the American side. They have the actual hydro dams, and we divert the water there and we let it go down. And I want you to think about those hydro dams. How do we generate electricity? And in Ontario and Quebec, most of our energy comes from renewable sources. In Ontario, we have a lot of hydroelectric power. We also have some nuclear power, wind power growing. We burn almost nothing to make electricity in Ontario. In fact, on most days, we burn actually nothing. Our electricity is entirely clean, entirely renewable. Nuclear has its cleanliness concerns, but there's no emissions from it. But hydropower, how does it work? How do we turn falling water into power?
Doesn't it kind of like a story that you told us about like the guy who lift the rock up in the air?
Yeah. The thing you have to think is that it took a tremendous amount of energy to get the water up the escarpment. Now, where did that energy come from? How'd the water get up above the falls? Do like the citizens of Niagara Falls get buckets and like truck it up all day and they like keep this thing running?
Damn right they did.
Felt like it some days living in Niagara Falls, but no. Who does all that hard work?
It's the Rain Man.
The sun! The sun does all the hard work. He shines down on Lake Ontario, and Lake Ontario goes, okay, Mr. Sun, here's some water molecules, and they float up into the air, and they float up there, and then the sun heats up some air over here and cools it down over there, and so you get pressure differentials, and wind moves, and it carries all that oxygen with us, and then eventually you get enough water up in there that it just starts falling down, and we call that rain or snow, depending on what kind of year it is, and it falls above the escarpment, and it runs through different rivers and creeks and aquifers, and it makes its way down the Chippewa Creek and the Welland River and all these things until eventually it gets to the Niagara River, or it gets to Lake Erie, which also feeds into the Niagara River, and it makes its way back to the falls. And it's weird to think about, but every ounce of water that falls down that falls has to then get evaporated by the sun and move back upstream for it to be able to fall down again. Does that make sense? So, weird to think about, but a hydro plant is really a solar plant, right? We're really harvesting solar energy. We're doing it in a different way. We're saying to the sun, hey sun, move a bunch of water, and then we just put a turbine on. We just put a gear there so that as the water flows through this pipe, it makes something turn. We attach some magnets to that. We put wires around it, and as the magnets spin, they move electrons through the wires, and we call that electricity. So, that's it. That's the process. We are using natural principles. We're using the natural tendency of gravity to bend space and time and pull water to a lower space from a higher space to generate energy. Now, that energy doesn't come for free. Something has to provide it. And in our case, the sun provides it. And if the sun stopped shining, rain would stop falling, and there'd be no water upriver, and Niagara Falls would stop. We'd also have some other problems on our hands. Yeah.
Mind equals blown.
Yeah. Right? Just a big solar power plant in a different guise. So now I'm very mind-blowing. Why mention this? Well, that power plant is the exact same principle as the electron transport chain, where instead of hunting down individual NADH molecules and having to have an enzyme that also finds an ADP, gets them both in the same spot, binds them both, and then says, okay, now that we've got you together, oh, actually, it turns out an NADH has enough energy to phosphorylate 3 ATPs, so we would have to find an NADH and 3 ADPs, bind them all in place, and then do that. That could be what the cell does. But because it has to do this so frequently, it designs a different system. And what it says is, let's take our NADHs and our FADH2s, and let's get the energy out of them, and let's temporarily store that in a different way. Let's truck the water up the hill, as it were. Now, this doesn't move the water, but it operates on the principle of osmosis and diffusion. Can somebody remind me about those two things, osmosis and diffusion? What were those principles about? Anyone remember? Diffusion means that if I have a petri dish here and I put a little food coloring in the middle, what's it naturally going to do? Spread it out. But osmosis says, if I stop that food coloring from moving, if I put a membrane around it that won't let food coloring through, what's going to happen, or won't let salt through, say, or won't let won't let sugar through? What will water do to try to compensate through it if it can move through the membrane?
It'll go in there and try to spread out the wall.
Yeah. So water moves across a membrane, and things try to move across a membrane to try to spread things out. So here's what the cell does. There is a series of molecules embedded in the membrane of the inner membrane of the mitochondrion. And down here is the matrix, and up here is the inner membrane space. Intermembrane space. Intermembrane space. And what we do is these enzymes don't bother trying to grab an NADH and 3 ADPs. Rather, they grab an NADH and they oxidize it. Now, we haven't talked about this since Unit 1, but I want you to look here. Because I've thrown these reactions at you, but now take a good, careful look. We take NADH and we oxidize it. That's a type of reaction. We learned about oxidation and reduction reactions last unit. But along the way, it turns into NAD plus and H plus. Now, if you've taken my chemistry class, you've heard me say this 100 times, but I probably said here too, especially if you took grade 12 chemistry with me. Chemistry is all about what part of the atom? Electrons. It's all about electrons. Well, let's pay close attention to electrons here. NADH, which has no charge, becomes NAD plus, which is positive, and H plus, which is also positive. How do we take a neutral thing and make two positive things? What had to happen? And this might be easier if you're in my chemistry class right now, because we think a lot about how do you take something that's neutral and make it positive? What does it have to do? Yeah. In fact, if you remember, we had this acronym, this stupid acronym, oil rig, but oxidizing is losing electrons. You can also say that Leo the lion goes grr. Lose electrons, oxidation. Gain electrons, reduction. But regardless, this is an This is an oxidation reaction, and I hate this diagram because it doesn't plainly show this, but this is all about electrons. And what happens is, how many electrons did this NADH obviously get taken from it? It went from having no charge to this having a positive charge and that having a positive charge. How many electrons did we lose? Beautiful. Exactly right. So it takes 2 electrons and releases them. This is now done with. It will float away. This can float back to where the Krebs cycle is happening and be used again to be recharged. Does that make sense? NADH is done. It's dealt with. But its electrons have all the energy in it that it has given up. All the delta G is in these electrons. And then there's enough energy in that electron to operate 3 pumps. And you can see them here. There's one, there's another, there's a third one. And so the electrons, this first enzyme, that is a transmembrane channel protein, that is also an enzyme down here, it catalyzes this reaction. So it makes the NADH give up its electrons and release NAD plus and H plus. And then it takes this H plus and it actually pumps it through the membrane. Now, to be honest, it doesn't have to be that H plus. If you've taken grade 12 chemistry and we got to acid-base chemistry, which I don't know if I did the last time I taught it because I didn't get very far because of COVID, but if we taught that properly, you'd know that water is always full of H plus and OH minus. There's always some H plus in water at all times. So there's lots of H plus to be found. It's easy to find. But regardless, this pumps an H plus ion into the intermembrane space out of the matrix. And then those electrons get passed along. There's this carrier molecule called quinone, but it just acts as a carrier, and it gets the electrons to this second enzyme called cytochrome B. And cytochrome B uses more of the energy from those electrons and pumps another H plus ion into the intermembrane space. And then those electrons get passed on to this, which is called the cytochrome C complex. It is not a pump, it's just a carrier. It actually lives on the intermembrane side, but it will carry those electrons onto complex 4, this final protein, and it also pumps an H plus up through the membrane. All right. Now, at the same time, for this to happen, it also takes a couple H pluses that are floating around in here and reacts them with an oxygen molecule. By the way, do you see the nasty little chemistry they're giving us here? Love this. Yeah, so what actually happens is it has to wait until there's 4 H pluses and we actually get 2 waters at the end. But they're just kind of cheating and showing it as if it can react with half an oxygen molecule. That can't actually happen. If we were actually balancing this equation, it would look like this. But it is considered acceptable to use fractional values for oxygen to keep things simpler, but I've never loved it. It's perfectly acceptable form, but I think it's skeezy. Anyway, and it takes oxygen and converts it into water. Now, this is important because what do we know one of the products of cellular respiration is? We know we get water out, right? So this is the water that gets produced.
This is
Well, we're going to talk about that. It's a good question. Why bother with this? Well, the answer is that the little tiny Niagara Falls elves are humping water up the escarpment, and they're pouring it into the Niagara River up top. What we are doing here is we're carrying big old buckets of water, and we're piling the water high up on the land here, and we're taking it out of the lake down here. And what's that water going to want to do? It's going to want to fall back. But we have a dam in the form of the membrane. Do charged ions move well through a phospholipid bilayer? No, in fact, they're the least able thing to move through because this whole intersection of it is nonpolar, right? So we are pumping H plus ions outside of the matrix, and then at the same time, we are getting rid of H plus ions inside the matrix. You see that there? We're using the energy from NADH to pump 3 H plus ions up out of the membrane, and at the same time, to get rid of 2 H plus ions from inside. That's a net shift, if you think about it. It's a big net difference, because the inside has gotten 5 negative more. Does that make sense? 5 charges more negative, because 3 H pluses left and 2 got reacted away. So altogether, the inside of the membrane is -5 compared to where it was before. And what's the outside of the membrane? +3. That's a net shift of 8. Does that make sense? We're making a big difference every time we oxidize an NADH. That might be worth writing down just really quickly. Every NADH to NAD plus H plus reaction gives 2 electrons, which are used to pump 3 H pluses from the matrix to the intermembrane space. And in the end, where do the electrons go? Well, they join up with this oxygen and these 2 H pluses to make water. Because if you look here, just think, could you take a positive thing and add it to a neutral thing and get a neutral thing? 2 H pluses plus half an O2 should give you H2O with 2 positive charges, right? But it doesn't, because this is the resting place for those 2 electrons. And so the place where the electrons end up is in the water. So, and 2 react 2 H pluses from the matrix with oxygen to form water. And the result of this is the matrix takes on a -5 charge, and the intermembrane space takes on a +3 charge, an overall shift of 8. Take a minute and write that down. I don't want to rush you. This is a big concept. It's heady. It's confusing. It's complicated. And so am I, which probably doesn't help. So it's kind of like saying, hey, if we had energy stored up in Niagara Falls, that we wanted to get into our power grid, one way we could get it into our power grid would be to use that energy to pump a bunch of water up to the top of the Niagara River. Now the Niagara River would have a stronger flow. There'd be more water to go through our turbines, and we could produce more electricity. Does that kind of make sense as an analogy? That's what we're saying here, is what if we moved a bunch of water up the Niagara River so it could flow through the hydroelectric dam and give us energy. Here, we take an NADH and we pump a bunch of H pluses from the matrix to the inner membrane space. And then, to top it off, we use up 2 more H pluses. What we have made here is the formation of what we call a chemiosmotic gradient. This forms a chemiosmotic potential gradient. What the hell does that mean? Well, I'm glad you asked. Because what it means is this. If we have the membrane here, and we said down here is the matrix, and up here is the intermembrane space, well, we've now changed a bunch of things. Because we've said this side is really positive, and this side is less positive. So we have a charge difference. We have a charge gradient. But it's not just a charge gradient we have, because we also just have more H plus ions here, specifically H plus, and we have fewer here. That is a chemical gradient that's going to want to result in diffusion. Because we know from the principle of entropy that if one molecule is concentrated, nature wants it to spread out. So there are 2, and then there's just the overall concentration of it. We also have the fact that this ends up being a lower water concentration, and this being a higher water concentration. And this gives us an osmotic potential, an osmotic gradient. And all 3 of these things are making it so those H plus ions have a ton of force trying to push them back into the matrix. Just like if we go pile water up the Niagara River and set up a dam, which we can do, by the way. Has anyone ever seen the footage of when they shut off the falls in the 60s to do some structural work? Have you seen these pictures? It's incredible. It's crazy to see. But they could do it tomorrow if they wanted to. We could divert all the water to the hydroelectric plant, and we could literally stop the flow down the Niagara River. We could also dam that up and just stop the flow completely if we felt so inclined. Of course, we would stop generating power. That one goes to Bing right now, and it's driving me crazy. Dammed up Niagara Falls, 1960s. I think it's the 60s. Yeah, 1969. So if you look here, they dammed it all up, and there is the top of the falls with essentially no water running down. I mean, you can see there's a little trickle there, but basically just shut right down. And that's the Niagara River. Pretty crazy, right? And you can see they went in with some heavy equipment, and they were doing some work to kind of do some restorative work and keep it from eroding in an undesirable way. Of course, the falls does erode. It moves back like, what is it, a foot every year, I think they say? A couple of feet every year, which is crazy to think. But all that water, of course, moves rock. And they shut down the U.S. falls as well. So it's also really notable to see the big old pile of rocks? That's because the water is just constantly tearing away at that rock face, right? And eventually, it will just make its way all the way back to the lake. You know, eventually eventually then in theory, the water should just kind of level out, which would mean that, you know, the level of Lake Erie would drop substantially. It's gonna be a long time from now. We'll probably have destroyed the planet by then, so we probably don't have to worry about it. That was darker than I meant it to be. That's probably true, but pretty crazy, right? So that is the equivalent here. This right here, which if you grew up living in Niagara Falls is kind of a crazy picture, is the equivalent of what the electron transport chain is doing in the cell. It's taking NADH and it is using the 2 electrons from it to store the delta G, to store the free energy that it got from Krebs cycle, and it uses that to actuate 3 pumps: complex 1, complex 3, and complex 4. That's right. Complexes 1, 3, and 4 are the pumps. What is complex 2? If complex 1, 3, and 4 are the pumps, why do we need this complex 2? Well, what do you note?
You get to the complex.
Yep, so in part, but no, because quinone does that. Complex 2 is this enzyme here. And what's that enzyme doing? Let's zoom in on it. What does complex 2 take care of? Complex 1 takes care of NADH. Complex 2 takes care of FADH2. And the thing to know about FADH2, it also gives up 2 electrons, but FADH2's electrons only have enough energy to actuate not 3 pumps, but how many? Look here, electrons enter here. They go through quinone to complex 3, through cytochrome C to complex 4. How many H pluses do you get from an FADH2? Not 3 of them, just 2. Does that make sense? Because FADH2 has less energy than NADH. So it has to enter the process further along, and it moves fewer H pluses. But everything else is the same. Those 2 electrons will still eat up 2 more H pluses in the matrix, forming water. So that's worth mentioning. FADH, and we can put that on the big H plus pump on the next one. FADH2 to FAD plus H plus, or FADH plus H plus, happens at complex 2. Osmotic, which is just the adjectival form of osmosis. Happens at complex 2, basically skips complex 1. So it can only move 2 H pluses and uses 2 more to form water. So FADH has less energy than NADH. 2/3 as much. Complexes 1. Oh, I lied. I was going to say 2, but I meant to say 3. 1, 3, and 4 are the H plus pumps. 1 each per pair of electrons. And it's at the end of the chain the 2 electrons form water. And the actual reaction there would be 2 H pluses plus 2 electrons plus half of an oxygen molecule gives you a water molecule. Obviously, in reality, you'd have to double that whole equation because there's no such thing as half of an oxygen molecule. But we do it this way to show, oh, did I just say electron? But of course, how many electrons are there? 2. It's a pair of electrons. The other thing you'll learn in chemistry is that electrons often move in pairs. Not always. Of course, we know when we form ionic compounds, you can move in 1s or 2s or 3s or any other thing. But frequently move in pairs. In the next space, I'm just going to more cleanly draw what I drew kind of ugly up there. So I'm going to start doing that because I'm bad at drawing. But take your time, please. Oh God, it already looks terrible. That didn't take long. By the way, I tend to draw the matrix as the bottom and the intermembrane space as the top, but there's nothing magical about that. It's just kind of my habit, and you'll see textbook diagrams that switch it. So you'll have here H plus ions moving through the membrane. And what we end up with is a high concentration of H plus. And if you haven't taken chemistry, I know I mentioned it once in this course, but what do I mean when I put square brackets around something? Concentration, good. And what does concentration mean, actually? That might be worth mentioning. Yeah, stuff dissolved in stuff. So this is lots of H plus dissolved in the water. This is a low amount of H plus. And of course, what's going to be the overall charge out here? The overall charge is positive. And the overall charge in here will be what? Very good. And so this makes what we call an electrochemical gradient. That's the other term we can use for this. All right? We say it creates chemiosmotic pressure, or a chemiosmotic gradient. That's true. The other term you'll see used is an electrochemical gradient. Basically, what does that mean? It means the H plus ions have a huge force pushing them towards the matrix, but they're blocked. How does the cell take advantage of this? Well, the first thing you'll note is that for some reason I had this paragraph span 2 pages because I'm a pro. A lot of lesser teachers would have put that all on the same page. Chumps. Cowards. They think you can't read between 2 pages. They don't trust you. Me? I trust you. I have faith in you.
I'm sure that's why that happened.
Yeah. I was like, do I want to make this easy for them and put all that text in one spot? No. Oh, no. No. I'm going to divide it between 2 pages. Like a pro. Like a man who gets paid almost $100,000 a year to do this. You know? Who is proud of his work and who would proudly display it as being well worth the money invested by the taxpayers of Ontario. Yeah. No, nothing embarrassing about that. No, I should have put this on the wall for parent-teacher interviews last night and said, look at the work I do. Look at me. Praise me. Be amazed by me. Right next to my salary. God. Anyway, enough of my self-loathing. Let's talk about this paragraph, conveniently divided between pages for your viewing pleasure. Since there's a large force of attraction for those H plus ions to move back into the mitochondrial matrix, the cell can harness the energy of the ions as they move. And I swear to God, look at me. This isn't even an analogy. It's just a generator. Remember I said that Niagara Falls, at the bottom, they have a turbine, and it's literally like fan blades that as the water flows through it, it has to spin, right? And then that's connected to a permanent magnet. It's mounted inside of a bunch of coiled wires, and as that spins, it makes electricity. Well, I swear to God, they use the same principle, which is they have those H plus ions fly through, and there's a protein at the bottom that legitimately spins like a generator. This has been demonstrated, and I'll find the footage and show you. It's super cool. And how they discovered that is also super cool. We'll get there in a minute. And in the process, it catalyzes the reaction of ADP into ATP. So what we make is a hydroelectric dam where we pump a bunch of H plus ions out into the intermembrane space, and then we don't let them through because the membrane won't let them through. And then what we do is in a few key places, we put a channel protein that they can go through. Well, what are all those H plus ions going to do? Well, just like the Niagara River finds the turbine channels and goes to the turbines, the H plus ions are going to find that protein channel, and because of all the osmotic pressure and the chemical pressure and the electrochemical gradient, they're going to fly through that thing with a ton of energy. Does that make sense? And when they do, we can capture that energy and we can use that energy as a free energy change, and this molecule is called ATP synthase. ATP synthase. Hopefully, its function is pretty clear to you given its name. It synthesizes ATP. So here's some diagrams of it. And this is kind of a schematic diagram of it. And then if you look over here, you can see that this animation I'm about to show you works backwards. They have the intermembrane space on the bottom, and they have the matrix up above. And you can tell that because I don't know if you can see this, but I can see this. There's a bunch of little H plus ions down here, and there aren't many up there. But this is an actual space-filling model of the ATP synthase complex. It has the transmembrane portion, what they call the F0 portion, that's embedded in the membrane. By the way, what would the amino acids that form this part of it probably be like? They'd probably be nonpolar, right? Like highly hydrophobic. And then here we have the hydrophilic generator portion of it. And if we actually watch this animation, and if we just watch this animation, and I'm not actually going to watch the whole thing, though this is very much worth watching, and it's in here, but you can see it actually physically moves like that. So let's see if we can get to seeing it in action. So if you look here, what happens is it works as a channel protein, and it allows H pluses to fly through, and as it does, the molecule actually physically rotates to capture that energy. And then the physical torsion of the molecule is then used to catalyze the reaction. Does that make sense? It's mechanical. So it is a physical, mechanical enzyme, which a lot of enzymes are. It works by motion. And I know this may look like a cheap graphic, but this isn't just a graphic. It's actually a simulation. There's actually math going on in this showing what happens. But you can see there's an ADP being phosphorylated into an ATP. And if you watch from this side, you can see that when all the business of doing is done, it takes that ADP, finds a phosphate group, and turns it into an ATP. It's a physical motor. So again, we're not going to watch this all right now, though I strongly recommend that you do. I also put a second video up here that shows the whole process. And it's done by the same research group, if I'm not mistaken. And again, if we just watch this video. Oh, no, sorry, this one's from Harvard University. That's right. So here we can actually see the mitochondria in this picture of a cell. And if, yeah, the mitochondria. There one is. See it? And you can see the inner membrane, and you can see the folds of it, which are called what again? This way. And now we get to this highly accurate animation. You can see the chemiosmotic gradient, right? We've got all these H plus ions, which by the way are just protons, in the inner membrane space, and the matrix is largely devoid of them. And look again, you can see that it's actually a mechanical action. It is the torsion of this thing that provides the delta G, that provides the free energy to phosphorylate ADP into ATP. So I will commend that to your walking. But if you look, they actually use, has anyone ever built electric motors here? Anyone in like tech class done anything with motors? Because rotor and stator are exactly the words we use for an electric motor. The rotor is the part that rotates, and the stator is where the permanent magnets are. Now, this is not magnetic, but they're using that language because it really uses a similar process where this portion of the molecule actually rotates, and then that torsion provides energy into these complexes here that can allow them to take an ADP that they've bound, phosphorylate it, and produce ATP. Long story short, no. But don't worry, I'll print it out for you. But here's the basic idea. We call this the chemiosmotic hypothesis. And the chemiosmotic hypothesis, in short, says this. NADH and FADH2 are used to pump H plus ions out of the matrix. As they flow back into the matrix, through the ATP synthase molecule.
Okay, but there's not just one of these, right?
Oh no, they're all throughout the membrane. And remember, we said one of the reasons that there's a big folded inner membrane is that gives you more spaces to put these things. If you just have a single looped membrane, you'd have way less space for these. These are all throughout. The mitochondrion only has one job, and it's to do this. As they flow back into the matrix through the ATP synthase, each H plus ion provides the energy to take an ADP and phosphorylate it to form an ATP, and that is now ready for the cell to use as energy. So the mitochondrion is just a big factory. It's a big factory that takes sugars and other metabolites, breaks them down, gets the energy out of them, and eventually turns all that energy into ATP. Some of that ATP is formed directly, but most of Krebs' cycle puts energy out in the form of NADH and FADH2, which are then used to run this process. And this is called oxidative phosphorylation. Oxidative phosphorylation. That's an I, not a Y. It's okay, I teach this. Earning my pay, team. Called oxidative phosphorylation because the electron transport chain dumps its electrons into oxygen to form water. And if that didn't happen, the electron transport chain would back up. So if you don't have oxygen, the electrons can't get out of the chain. And if the electrons can't get out of the chain, you can't put new electrons into the chain. If you can't put new electrons into the chain, the pumps stop. And if the pumps stop, H plus stops getting pumped out of the matrix, which means they stop falling back into the matrix, which means that beautiful ATP synthase clown head of a molecule stops spinning, which means we stop producing ATP, which means our cells don't have energy, which means we die. Which is why if you don't breathe oxygen constantly, you'll die. Because your cells won't have oxygen to grab the electrons from the end of the electron transport chain, and the whole system stops.
I can't believe you'd call it a clown.
It does kind of look like one, doesn't it? Especially in the one diagram where that's on the top, not the bottom. So we will talk about a little bit of accounting on Monday. We're going to do a little lab. One thing I know we're going to do this week is we're going to do a little osmosis lab where we use some dialysis tubing and kind of learn how osmosis works. Guys, have a wonderful weekend. Thanks for putting up with me being long, drawn out, confusing, and texty here. But listen, Read the textbook section on this. You want to understand this. You want to understand this real good. How good? Real good. Kind of good?
No.
Real good. Hi. I'm doing great. How are you? Yeah, what can I do for you? Hi. Sure, let's take a look. Is it an iPhone?
iPhone.
Oh, so you definitely can. We're just having an issue probably. So here's what I'm going to do. Probably you're just, without realizing it, getting your password wrong. And probably it got stored in there. And so then you've got a bad password in there. So I'm just going to try another one that I know works, and we'll see if that gets you there. And if it does, then we'll know that was just a password issue. Oh, interesting. So
It's not a password.
So it could be a device side issue then. Now, there's two possibilities there. And you don't have a proxy that you're trying to run, like you didn't have a proxy on, so you're like, I'm going to run Snapchat, because that'll make it not connect. Private Wi-Fi address. It won't let you have a private Wi-Fi address, because you're not allowed to be private on a network, because the board wants to track everything you do. So if you do anything inappropriate, they can be like, this was the device that did it. So yeah, they don't like private connections. I think now that we've turned that off.
What? I've been paying.
Yes. Many.
Interesting. Alright. Now it could be automatic. Yeah. Automatic. Off.
Give it a try back.
That's really weird. Okay, let's for the sake of argument. Try me. It could also just be every once in a while they update the security protocols for the board, and it takes them a while to get devices signed up. So it could also just be that they've changed like the login protocol, and it'll be a week or two before certain iPhones are able to attach. In which case, hopefully, when you get back next week, it'll attach. Yeah. Yeah, so that's let me, I need to remember my password.
Sorry, did you have a question for us?
Like, no, because I'll get like really mad because it just doesn't
Okay,
work.
you're on.
Like,
Now,
I'll shake my head.
something
But then I
further.
realize I'm
You're on
like,
signed in with my account, which is fine, but all of which is to say if you're doing anything inappropriate on there, I'm going to hear all about it. So keep it clean, all right? Because I don't want to hear all about it. So, all right, so keep it appropriate.
And then when she needs build, when you don't use the building, what happens? It's all.
You'll be fine. When you get back, it'll come. But what I want you to do, it'll keep connecting for you, but you don't want me being able to see everything you do on the internet, I'm assuming. So in about a week's time, come on back down and we'll get you signed in under you, okay?
On Monday, we'll come back.
And again, just be mindful of that. Anything you're doing on there, I can see. So don't make me see things I don't want to see, all right? Please, for God's sake.
Thank you, Mr.
Yep. Yep.
I had that for
Did you have the Dora haircut?
Yeah.
I love the Dora haircut.
I don't.